Lesson 1-5, Acceleration. Acceleration is the rate of change of velocity. So it's the change in velocity over time. Now remember, change in is always final minus initial. So if we say let's make some things. Let's say t0 is 0. And let's say Vf is just V. If I take this equation, we'd end up with that. If t0 was 0, and the Vf was just V, multiply by t, and then add the V0, you get that the final velocity is the acceleration times time plus the initial velocity. That's that last equation there. Acceleration is a vector. It's positive or negative, and the unit is in meters per second squared. Because the unit on the top is meters per second, the unit on the bottom is seconds. Divide fractions by multiplying by the reciprocal, and you get meters per second squared. If the acceleration is in the same direction as the motion, then the object is increasing speed. So on our first case, our car is traveling forward and acceleration forward. So this car is speeding up forward. In the last one, the car is going backwards and accelerating backwards. So this one is also speeding up. If the acceleration is opposite direction as the motion, then the object is decreasing speed. So in picture B, the car is going forward but accelerating backwards, so that means it is slowing down. In picture C, the car is traveling backwards but accelerating forwards. Since those are opposite directions, it is also slowing down. A horse starts running. If it goes from 0 to 55 kilometers per hour in 3.5 seconds, what is the horse's acceleration? Well, it doesn't specify this. Let's go ahead and convert the kilometers per hour into meters per second. So 55 kilometers per hour. Kilometers is on top, so I'll put kilometers on bottom. So it cancels out. And kilo is 10 to the third. That always goes with the base unit. And then I don't want hours, I want seconds. So hours is on bottom, so I'll put hours on top. Seconds is on bottom. 3,600 seconds is 1 hour. Run that through my calculator and I get about 15.278 meters per second. So, this is our initial velocity, final velocity. This will be our change in time. So our acceleration is our final velocity minus the initial velocity over our final time minus initial time. So our final velocity in meters per second was the 15.278. The initial was 0. And our change in time was 3.5 seconds, or 3.5 minus 0, which gives you 4.37 meters per second squared. So this horse is changing its velocity by 4.37 meters per second every second. A car slows from 15 meters per second to 10 meters per second by an acceleration of 4 meters per second squared. How much time did it take to slow down? All right, so I have my acceleration, I have my initial velocity, my final velocity, and I'm looking for time. So I can use my acceleration formula. Remember, acceleration is change in velocity over change in time, and it's always, change in is always final minus initial. So our acceleration is 4 meters per second squared. But it is slowing down. Since it was going forward and slows down, this acceleration has to be negative because the car goes forward but is slowing down, so the acceleration has to be negative. Final velocity is 10 meters per second. Initial velocity is 15 meters per second. And we're looking for our change in time. So let's just call it change in time. So we could put this over 1 and cross multiply. So my change in time looks like it's negative 5 meters per second divided by negative 4 meters per second squared, which would be 5/4 or 1.25. Now let's look at our units. Meters per second divided by meters per second squared. Multiply by the reciprocal. See, the m's cancel, and one of the s's cancels, leaving just seconds, which is time, which is what we'd expect. Often things have constant acceleration or near constant acceleration. If there is constant acceleration, the graph of a position versus time is parabolic. And you end up with a nice quadratic equation. The graph of a velocity versus time is linear because the acceleration is always the same. It means the slope has to always be the same. And the graph of the acceleration time is constant because the acceleration is constant.